already have a show that I'm watching that's 12,000, 1,200.
Yeah, I was gonna say, no way, you're with
True. I've been basically taking, like, you can get screwed up.
Do you know what I did? Oh my god. Wait,
I just started game time.
That's my concern.
I have to finish house first. No, once I finish house,
Recovering from my sickness now.
Are you feeling better?
I think, yeah. I got like literally my chest
like actually or say nothing. Or say none. I like to say and I think it's I was really hoping that like it tells you your life and then when we're stealing you. Oh, I don't have
No way we're getting
it says 15.
Okay, why does this type of thing happen on Saturday?
That's what I'm saying.
It
It's
could
literally
be any other weekend except
So I think we have a wire.
We will get buried. The great flood.
You have to dig the car out. What day? What day?
This is gonna be a catch-up class, so we're gonna go over a bunch of stuff that we didn't get the chance to go over in the lab that I want to go over. How do people feel about the lab? Do you have a working solution to the lab? No. Why were you not at office hours?
Because I have a class after this.
Yeah. Okay. So there was office hours online. I did all day Wednesday.
No, I was working for something.
All right. You need to get with me after because you need a working solution on the lab. Does anybody else not have a working solution or understanding of the lab as we went over it?
Oh, yeah.
2, 1, 2, 3, 4. All right. I need to see you all because you all need to have a working understanding of that lab in order to do the homeworks. Right? Has anybody looked at the homeworks yet? Some people I know have. Right? Did you do? How many did you get here?
The question I did the first one, but then like some of the questions I didn't understand very much.
Some of the questions you didn't understand very well. Okay. You wanna you recall which ones you didn't understand?
Like you talked about right what where primitive.
Yes.
I looked that up online, but I couldn't really understand.
Okay.
You nerd about
So real quick, let me cover this one question on the first homework, which is the reference to a write what where. So you did the homework, right? You made it work?
I tried.
Okay. What you ended up getting in that first homework is the ability to write whatever you want, wherever you want to write it, in absolute terms. Absolute as in it's not a relative pointer, it's an absolute memory address, 4 bytes, right? That's what you're looking to get out of that first lab, and that's what I mean by write what where. It is the name of a primitive, and a primitive is a piece of functionality that you build out of flaws in the program, right? So we are not taking a single bug and getting control. We are taking a single bug, we're turning it into a primitive, a piece of programming that we can use one time or multiple times, and using that to take control. So, good question. There are 2 examples in that homework, EX1 and EX2. EX1, everyone should be able to do, and I will expect you to. EX2, I don't expect everyone to be able to do. And so, I want you to turn in your effort, your understanding, a write-up of where you get, right? Part of the trouble setting up this class is that I have 20 people as grad students currently, and then I've got a bunch of people who are freshmen, right, who are still struggling with the lab. And so trying to tailor that together is a little bit difficult, which is why I've given you those kind of disparate examples. Can't get number 2, don't worry, we'll go through it. Let's talk about shellcode. I wanted to do this later in the class, but I'm reordering due to both snow days and also making sure that you have what you need to understand in order to get these homeworks done and feel comfortable in the lab. So I'm going to move shellcode up a little bit, and we're going to walk through what the shellcode is. So the reason that I moved it up is because I had one student, I'm not calling you out, this is on me for not explaining this. And what happened was, let's do this with /R, Thank you, Joyce. Sorry. Okay. So in the shell code that you guys had, if you pull that up at make Python, you can see that it starts with that EB1F58, right? If you take a look at that. And I told you, in order to put a trap at the front of this, so debug breaks when your shell code runs, you put in add a /x cc, right? Because the cc byte, single byte cc, is the trap instruction opcode. So 0xcc is the trap. And we talked about how the debugger uses trap, not trar, that's not a word. We talked about how the debugger uses that to overwrite bytes in the actual code page and then replace them to get it run before. That's how the debugger does software breakpoints. There are also hardware breakpoints. Those are individual registers, pieces of hardware. They're limited in number. Software breakpoints are unlimited. They can make that table grow just fine. The way the hardware breakpoints work is whenever the computer goes to that, goes through the bus to get to memory, it checks all those registers. And if it is doing a read or a write or execution on those code pages, those hardware breaks will go off. Now, they give you a lot more power. This guy here only works for execution, right? It's an opcode. The hardware breakpoints let you say, if anybody writes here, let me know, okay? If anybody reads from here, let me know, okay? And when we get into heap stuff later on, we'll make that clear. So the problem that this student was having is that rather than adding the CC above this, and I'll show you that it's there. This one. Yeah. So you can kind of see that it's right here. Anytime you do a break, EIP still moves down, right? So when I did this as EIP, it did not show you the trap, but it's still there. This student had replaced the EB with the CC, and so now EIP was pointing right here at 1F. So they had misaligned the instruction by 1 byte, and they got a seg fault, okay? Right? And so what was happening is the processor is interpreting 1F5E8976 as some other instruction, and in this case, that instruction did a bad read, caused a seg fault, okay? Their logic on the actual solution of the problem was spot on, but their misunderstanding of the shell code, because I didn't go over it, was not quite there. So let's talk about what this shell code is doing. This shell code is an example of handwritten position-independent code, okay? That means this code runs without knowing where it is in memory. That's why we can inject it anywhere. Now, what it needs in order to run is an absolute address to its string, right? We're going to do a couple things here, and I'm going to break this out in a way that we usually do our breakdowns for functions, okay? So I will break it out like so. That's one block. That's a second block. Here's a block, and here's a block. So what do these guys do? There's a clever trick in here, and there's a couple ways you can pull this trick off. But it is a way of turning position-independent code, finding out where it is, and then using that for pointers. So what happens here, here's the trick. Right at the start of the shell code, this is a relative jump. It's not an absolute jump. It says, jump me forward X number of bytes. The X number of bytes it jumps you forward is the size of this code. It's going to jump us to the call, okay? So it's going to come down here and go to that instruction next, okay? That is a negative relative call. It will call EIP minus some number, and the number it's going to call us is back up to our shell code. Now, why would I want to do that? What are the two things that call does as an instruction?
This isn't relevant to that, but how do we know that's irrelevant though? Just by looking at the address.
Yeah, okay. So you actually will have to look here to find that, right? And know that you wrote this code, right? So when you look up jump in your Intel manual in volume 2, you've got, it shows you what the opcode is on the left. It'll say rel next to it, REL, okay? And you can write that manually in assembly, right? You can't do it manually in the compiler. The compiler will do its own interpretation, and it doesn't know that we want this code to be position independent. So when you're writing shell code, very often you're writing it, if it's going to be injected, you're writing it by hand in assembly so that you can pull these tricks, right? There are a couple tricks in here that you can only pull manually by writing to assembly, and you would do that using NASM, okay? Somebody else had their hand up for the answer.
It jumps, but crucially, it pushes the position of
Correct.
next instruction in the stack.
Yeah, it does two things. One, it changes the value of the IP. It moves to a new instruction, right? The other thing it does is it pushes the value of the next instruction immediately underneath it onto the stack so you can get back there. And that's an absolute pointer. So what we've done is put on the stack a pointer to this, whatever's right after it. And let's find out what's actually there. X space slash X. NSH. Okay, so if you look at your shell code in your Python script, you'll see at the very end it says binsh, right? That is what we put right at the end. So now we have an absolute pointer to the string, which we will need, okay? So there's one other problem that we're going to need to handle here, and that problem is that we need to have a bunch of nulls to call the functions we're going to call. This here, int 80, interrupt 80, you see it twice, is the equivalent of making a kernel call, okay? So just like if we were breaking this up, breaking the function up and we were looking for function calls that were library calls, these are library calls to the kernel, okay? And we'll talk about exactly how library calls to the kernel work in 1 second. But just know that's why I've broken those up into 2 blocks. Now, in order to make those calls, we need to have a bunch of nulls in the data, okay? We're going to need zeros sitting around. The first 0 we need is at the end of binsh. Right? We've got to null terminate that string. Otherwise, the computer is going to be like, when does the string stop? I don't know. As soon as we get to the next random null that's in memory. Okay? So we got to put it there. Why can't we write it there in the shell code in the first place?
That would terminate your string.
It would terminate the string, right? We're using stir copy for the overflow. Stir copy is terminated at null. If there are spaces or zeros, you'll see that there's no zeros in these opcodes, right? That's another thing that I had to do manually, right? You have to write all of the code so there's no zeros in it. And so that's why you're going to see things like AL instead of EAX, right? EAX is a full 4-byte register reference. AX is a 2-byte register reference, the low 2-order bytes. Then you have also access to AL and AH, the lowest order byte and the secondest order byte cycle, right? So by moving, by zeroing out EAX, cleverly using XOR, EAX, EAX, doesn't matter what's in EAX, what's the value going to be after you XOR it with itself?
0.
It's always going to be 0, and the opcodes for that, lovely, don't contain a 0. So that's the way we make a 0, okay? And so once that's there, we can just manipulate the values of it, okay? So we've made ourselves a 0. We said, you can't really see it here, but this is pop ESI. So that means ESI is now containing a pointer to binsh, okay? So ESI is equal to a pointer to binsh. Okay? And so right here, what's that going to do? It's going to null terminate our string, right? The low order A, which is a 0, we're saying ESI is a pointer here. This is 0, 1, 2, 3, 4, 5, 6, 7. Put a null there. Now we have a null terminated string that we can use to call this function, okay? How do we know what function we're calling? The call is always int 80. How do we know? Well, it uses a fast call convention. This is specific to the kernel, specific to the Linux kernel, It will always be the same. If you look up a syscall table for Linux, 32-bit, 64 and 32 have different call tables. What you will see is that this number here is exev. That is a syscall where we can ask the kernel to execute a program for us. Anytime a program runs in the kernel, that's the way it gets run, right? What the kernel is a power broker for userland processes, okay? Your userland process is constrained in that in order to do something with the rest of the computer, to leave its own virtual memory space, to interact with hardware, to interact with the file system, it must work through the kernel, okay? It asks the kernel to do this work for it. The kernel looks at the privileges assigned to that process, to the user that ran the process, and it either says, here's the resource you want, or go squeak yourself. One of the two, okay? The way that you tell it is the value of EAX at the time of this interrupt call. That tells you what it is, and you look it up in the table. Now, on Unix, that table doesn't change, so we can call it directly. If we were looking at a different operating system, they may change. So Windows is the canonical example. Before Windows, SCO did it. The people who wrote SCO went and wrote Multics, and then they wrote the NT kernel. Same group of people. And when they did this, what they said is, our sys table is alphabetized. Anytime I add a system call to the kernel, it shifts everything after that. If I add an A call, every other one gets a +1 added to it, right? On Linux, they just tack it on to the end. It's a decision that the architects are able to make. So Windows shellcode, SCO shellcode, Multic shellcode, any NT kernel, the shellcode will be much larger because we have to resolve the functions in NTDLL and ask them to talk to the kernel for us. Otherwise, we'll guess wrong. Or it won't be portable by version, right? But on Unix, we can make the syscalls directly. That's what's happening here. Okay, so we've got a couple other arguments. We've got EBX, ECX, and EDX. Those syscalls have different arguments just like normal functions. The syscall dictates how many arguments it takes, okay? So EBX stores the string to the program we're trying to call. That's what's going to be loaded up and executed when we make this syscall, okay? And then we've got two more here, ECX and EDX. And those are our argc and argv. And so what we need to do is make the list of function pointers, and that's what we're doing here, okay? We're building it, and then we're going to make the call. And so when this happens right here, you've got your shell. It pops up. You see your $sign if you got it right, okay? So why do we do a bunch of other stuff here? Well, you've got, sorry, let me fix this block. You've got this stuff here, right? This was part of our trick. This is actually our string. This is the last part of the shellcode that gets executed, okay? And what this is going to do, we zero EBX. We put that in EAX, we increment it, so EAX is going to be what? 1. 0 plus 1 is 1. And then we're going to call the syscall 1 with a null EBX, okay? And what we have done there is syscall 1 is exit, and the value in EBX is the exit value. And so what we said is after the shell returns, and it comes back here, you're going to run exit on the program. If we didn't do that, what would happen to the program? It would crash. It might not segfault, but it would crash because what would happen is it would try to execute das and bound and a bunch of nonsense instructions that are what the processor interprets the string bin sh as, right? There's no such thing as code and data. Code is data, right? It's just hex bytes, and that's how this whole thing works, okay? So the shellcode does two things. It runs your shell, it runs exit. We do not want our programs to crash. What happens if a program crashes? What happens on Linux? I know you know. You built the fuzzer in the other class. What were you looking for when the fuzzer runs?
exit codes that aren't 0.
Exit codes, what else?
Oh, the systems.
The crash dump.
Yeah, the crash dump.
The crash dump, right? On Linux, the program crashes, it dumps core. What core is the memory space of the program, so that you can load it back up into a debugger and find out what happened. On Windows, what happens? Anyone familiar with Dr. Watson? Brian, are you familiar with Dr. Watson?
Yeah, I used it like 20 years ago.
It uses you. What happens is when a program crashes in Windows, it makes a crash dump, and then it sends it to Microsoft automatically without asking you. Now, Microsoft has a database of all the programs that have crashed, and why do they do this? It's not to catch hackers, it's to put pressure on third-party companies. Back in the day, Windows would crash all the goddamn time. And people would be like, Microsoft, your operating system sucks. And Microsoft would be like, you're running 400 third-party drivers that we have no control over. And that gives them the ability to be like, Adobe, your freaking TrueType font driver crashes 50 times a day on all of these systems. And then they can go and have a meeting with Adobe and beat them over the head with that. That's why it exists. Back in the day when Microsoft had security funding, which they don't anymore, there used to be 100 people on MSRC that would comb through those things and look for people like you doing untoward shit. Now there's 2. Where does the funding for security teams and operating systems come from in a company? It comes from the marketing department. Right? Comes from the marketing department. Okay? So sometimes there's a lot of workers, sometimes there's not. And it goes in cycles. Right? Oh, we solved that problem. We're not going to spend on that anymore. Where do we make spend up? Get rid of some of the marketing people. Right? Okay. So we don't want it to crash. We definitely don't want it to crash if we're writing kernel or browser bugs. Right? Anything that's spawning a thread, or anything where if the crash occurs, the whole computer goes away, it's not going to help you, right? Your shell is not going to function. Your persistence mechanism is not going to work. You're not going to be able to steal data off of it, right? And so what we're starting to get into here is what we call continuation of execution. And that is, you can't guess when you're doing exploitation because you need to know what you screwed up. You need to know exactly what the side effects of your exploit were, because you have to fix them in your shellcode, right? If you look at Metasploit, you are given kind of boilerplate shellcodes. Those are great. This is a boilerplate shellcode. But in real life, the very first thing you do before you run your boilerplate shellcode is fix everything you broke, right? And so you need to know where it was and what it looked like before you fixed it. Or you need to find a way to bypass that. So you have to have a great deal of understanding of the program, and that's where your reverse engineering comes in. Okay? And then further, you need to be able to write custom shellcode so that you can fix these things. And finally, you need to be super aware of what you have access to at crash time. Okay? Some of you have looked at ABO9, right? And people are pounding poor Leon for heap information. ABO9 is not a heap example. ABO9 teaches you 3 things, but it does not teach you how to own the heap. The reason it doesn't teach you how to own the heap is because it's extremely static. There's 2 mallocs and 1 free. That's not real life on the heap. If you knew you needed 2 mallocs and 1 free, you'd have done it on the stack. That's a static amount of data that you need, right? You use the heap when you're not sure until program runtime how much space you're going to need, right? We write that linked list for the grad project. You're going to have to use malloc or new, depending on if you're using C or C++, right? Because you don't know how many elements you're going to have to add to that list, okay? What ABO9 teaches you is how to learn how a complicated system works with no documentation. That is the DL malloc heap, which we will talk about after the midterm. We'll get deep into heaps then. It teaches you how to use an unlink bug, which is how do I turn a corrupted doubly linked list into a write what where, which is a universal technique that you can use. And then it teaches you how to clean up that heap so that stuff doesn't crash afterwards, right? but it's not actually a heap problem. The problem with a heap is taking a system that is constantly in motion, that you are blind to, and then turning it into a system that's deterministic. And that's a set of techniques that requires a set of primitives. Okay? And we'll get into that later on. Other questions that I had on the lab were, what does that /x do in Python? Why am I putting that /x in front of a number? And the reason that you're putting that /x in front of the number is that that is a Python convention and nothing else. What it says is, you got that /x EB in there. That's the first thing you see. You guys want to pull that up? Good. I'll pull it up actually. /xEB, right? When we looked at the memory, it was just the byte EB, right? What it tells Python is treat the next two ASCII characters you see, E and B, as a single hex number. So it's only going to be a byte, right? That's also why you got sys standout buffer write with a little binary thing here. If we tried to write it with print, it would turn it into Unicode. We don't want that. We just write the byte EB, right? That's all that's going on there with that /x. Okay. Does that make sense to everybody? It's just a way for us to write arbitrary hex to standard out. Other questions that we had. We are going to have to figure out some auto-grader stuff when we look at this because the VM that we gave you is not the VM that CSRF is going to put up there, and gadgets may move around because of that. The addresses that you're working with may be different. The other problem that I saw when I looked at gadgets is that on some operating systems, if you recompile it yourself, what you're going to end up with is a null byte in there. The way to solve that problem so that it's portable is put a nop in front of it. And so then if you use the byte, the address of the next instruction, there's no null in it. But if you're on a system that doesn't have that offset, you just hit the nop and fall through to the gadget you wanted anyway. So you can make it reliable in that way, right? And that is the introduction to nop sleds. I don't like people using nop sleds because they're unreliable. Here's why they're unreliable. If you have 256 bytes of space and your shellcode is 56 bytes, there's 200 bytes left for you to write a nop sled in. And a nop sled is a set of bytes that do something we don't care about. Any set of bytes that do things we don't care about, right? And what we care about is preserving the value of registers we need to use for continuation of execution later, right? But apart from that, it doesn't matter what it does. You will see people use the capital A as a nop. That's 41. It becomes inc ECX. If you don't care what's in ECX, increment it all day long. It's a nop. There is a nop that is 90. But if you write a whole bunch of 90s in your shellcode, white hats will catch you because they're looking for a whole bunch of 90s, right? If you want to be clever, you can recursively build an arbitrary nop sled. And the way that you do that is you say, the values that matter to me.
What is a whole bunch of 90s do?
Nothing. It's so if that's a trap, OX90 is actually an instruction nop. It just doesn't do anything, right? What it actually is there for is to fill the pipeline for processor optimization back in the day, but it still exists, okay? Okay, so let's say we're in a situation where we care about a set of registers. The registers we care about are ECX, EDX, and ESI. Those we can't change. We can modify anything else. What you do is you generate a random byte, and then you execute it, and then you see if those those registers changed. No, we're good. Generate another random byte, execute it. If you don't crash and you don't change those registers, fine. And you can do that as long as you like. And that is what the, if you look in Metasploit, that is what the random nop generator in Metasploit actually is doing, okay? So why would we do that? Well, we know already that the stack moves around sometimes, right? Due to our environment, different systems. You can tack that on the front and you can get 100 bytes plus or minus of leeway, right? Of randomness that you can work through. But you only get 100 bytes in either direction. And if someone's got a big environment on grade scope, it's just not going to work, right? It depends how different the system is, how many people have been on the system, the person you're owning, what have they been doing, what's their history file look like, what's their shell they're running. All that stuff matters, right? So in that situation, we don't want to use an ops sled. However, if we are looking at relative positions instead of absolute, sometimes they can be useful, right? You should not have to use them in any of the homeworks. If you do EX2, I will allow you to use a not sled, provided you are not jumping to it. You're jumping to a gadget that jumps into it. There are some reasons for that. It just saves you doing some negative math. Okay? Doing homework 2 requires you understand a number of things and a couple tricks. And so let's talk about the tricks that you need to understand to do number 2. The biggest one is understanding the very first mitigation historically that comes up, and that is a stacked canary, right? So when we looked at the stack for lab 1, it was argv pointer, argc pointer, ret to main, bold EBP, buffer space, and that's it. ESP is here. EBP is here at the top of the stack frame. Okay? And what we did is we wrote up from buff, we wrote 4 bytes for the EBP. We overwrote ret to a code page, jump ESP. ESP at the pop of ret is right here. That's the last thing we popped. And then we wrote our shell code right here, right? And that relied on us being able to get through all this and then exit the program without a crash house, okay? Here's what a stack canary does. It is the canary in the coal mine. Between your local variables and EBP, there's one other thing. So EBP is now here, and here is a canary. And the compiler puts that in. The operating system does not put that in. You can compile on a protected system without canaries. The programs that I compiled for you do not have a canary, so I wrote a manual canary for exercise 2. Normally what happens is _start, the symbol that a program always runs when it loads, it will generate a random canary before it passes on to main, and that canary is used for the whole program, okay? And what happens is, right before leave and ret, there's another instruction right before leave and ret. And what it does is it says, is the value here the same as the global stored random number that we generated under start? If it is, cool, nobody's corrupted us. If it's not, exit out, throw a signal, okay?
So that means the canary is the same for every stack frame?
Yep. Yep. Yeah. Because otherwise you would have however many stack frames you have, which is variable, especially if there's recursion, you would have to generate a new canary, right? Every time, and that's very expensive. And that table will grow indefinitely as well, right?
Would the actual solution change if you remove the -no canary or whatever in the make file? Because would the canary still be the top of the stack and we're just hopping over it? Like, if we didn't use the cookie canary that you manually
Yes,
set up
you
and just
could.
remove it
Yep.
from the make?
Yes, but the reason that I did not give you the other one and I'm giving you the manual one is so that you can see the code without having to reverse engineer glibc to really understand what's going on. It's a little bit more complicated the way they do it, but what I'm providing you, simple and understandable.
So I'm confused. What exactly is a canary again?
A canary is a 4-byte value that lives on a stack that is checked when a function exits to see if the stack frame has been corrupted or not. What I gave you, so I'll ask your question first.
Why is EBP pointing at the canary? Because won't it pop the canary into the base pointer for the prior frame?
So the work that gets done right before the exit takes care of it for you.
Is that a x86 convention?
No, it's fully done by the compiler. And so you may actually see EBP up here and have that be in the local space.
Okay.
It depends on your compiler. You can actually have a compiler that uses EBP as a standard register and doesn't denote the top of the stack frame. Like if it says no base pointer is the option, and from then all of the source code just needs to know where ESP is at any given moment, and then it works off of that. So if you see that later on, that's what's going on. It's rare and extremely obnoxious, and the reason you don't see it very often is developers who write code have to debug their own code, and they like to have a base pointer, right? That's why you don't see anti-debugging and anti-reverse engineering in real programs that aren't malware, because developers have to debug their own code, and developers are going to be worse debuggers than you are. They spend all their day developing. They don't spend their day in the debugger, okay? So they don't want to make it harder on themselves. It makes software less reliable, less understandable. Plus, you've got 100 people working on a program. Even if you understand it, 99 other people have to understand the code you wrote. And the more obfuscated it is, the harder it is to make money off of software, right? Let's see. So in the second example, I gave you the canary and I put a static value in there. I put a space in the static value. I put a null in the static value. What that means is you cannot write the canary. You have to bypass the canary. There's a couple ways that you can do that, okay? Later on, we're going to look at peaks. A peak is a specific type of info leak. A peak is leaking a pointer to a code page out of a program. That is the definition of a peak. It might be on the midterm. Okay, so what does that help us? It doesn't matter where in the code page we leak out the pointer, because it will always be the static offset from the start of the page. So if I leak out one pointer, I can be like, oh, I'm at 100 hex bytes from the start. Subtract 100, now I know where the thing is loaded. That's how we bypass ASLR. We'll get into that. I'm not doing that right here. We're going to start with the canary. The other way to bypass the canary is to hop over it. Okay? And the way that you're going to do that in that second homework, we will illustrate right now with a program that I wrote because Joyce asked a question. And this is more of a whodunit than a please own it. Let me see if I can find where I put it. Labs. Which one is it, Zoe? Lab Y?
That's the one you handed me.
All right. This is an extremely, extremely limited bug. Does anybody see the bug? It's right in here.
You sure? I mean, okay. The null byte.
What about it?
It writes after the 256 bytes because it's less than or equal to.
How do we index an array on a computer? What's the first index in an array? It's 0, right? So what's going on right here?
You're indexing 256 instead of like 255, which we want to do.
So it's an off by
1.
That is an off by 1 bug. It happens very often, and it's also very difficult to find. Why is it difficult to find an off by 1 bug? How come it only crashes when you put exactly the right amount of data in there, and no developer catches their off by 1 bugs?
They don't test for it?
Nope.
Because there's only one value where it'll actually trigger the error.
It's even worse than that. It has to do with memory alignment. When you ask for a value of memory that is not aligned on the word size of the processor aligns it for you, or the compiler will align it for you. You can't ask for 1 byte. You have to get 4 byte chunks, right? So if this is on the heap, and it's dynamically sized instead of 256, and there's an off by 1, there are only a very small set of values that will cause that program to crash. And it has to be 4-byte aligned so that the 5th byte is the off by 1, and it has to be actually abutting something that's going to be used. There was a bug in the Microsoft FTP client. That's what this bug is. This was a live bug on the heap in the Microsoft FTP client, and it must have been in 2007 or 2008, and everyone said it's not exploitable. And then Alex Soderov came along and owned it. And he didn't tell anybody how he did it either. He was like, I owned this thing, let's see if you can figure it out. Okay, and the answer is you have to make sure your byte alignment's correct, and you have to be sure you're controlling that something is on the heap right after it. We'll talk about how to do that later. But this is your off by 1, okay? What does the stack frame look like here? We have main calls vuln_func, and vuln_func has 1 argument, right? So there's arg1 to vuln_func, and then after that is the ret back to main, and then after that is going to be the old EBP for main. Okay, and then we're going to have our local buff. And this does happen to be aligned. That's why I did 256 specifically, so that would be exactly aligned. So when we write this off by 1 null, what are we going to hit?
Our old EBP.
We're going to hit the old EBP, the EBP that defines the base pointer for main, right? And we're only going to hit it with how many bytes? We don't get to control how many bytes we hit it with. It's going to be 1 byte. We don't get to control what the byte is. It's going to be 0. So the lower order byte of that pointer is just going to become 0. Can we own this bug? Yeah, we can, right? Here's what's going to happen. When we do this, EBP, instead of having some value in it, it will be 0, and so our stack frame will be misaligned, okay? And when we call leave on main, rather than moving EBP up into, when we call leave in vuln_func, rather than putting our stack frame at the top of the main frame, it'll be in the middle of buff, okay? So now when we reference our local variables, or we reference from ESP, we're going to be in the middle of buff, and we control that data. When you are looking at what you're doing, you are thinking, what do I know? What's predictable? What's not predictable? What do I control? What data can I put into this program? What data am I given by the program that I don't have control over, right? That's how you think about how this stuff works. And so what you get there when you pop ret is you pop it right out of buff. Okay, so let's try this, and we'll do the white hat route. We'll prove it's doable, but we won't bother with the shellcode. Once we get EIP, somebody's got to fix it.
I understand that like old EBP is like overridden a bit by the buff, right? But like, why does it leave it in like the function call instead of returning to main? I don't get that.
Let's walk through it. Let's do that. Let's see if Jeremy's solution works.
Wait, do you want my solution? Oh, is that?
I have it. I got it off your box earlier.
Okay. It should work. I mean, I definitely didn't know I did.
Well, we did it. You did it probably on a different operating system. This one is going to be operating system specific, right? This is why this is not a homework. This is like a let me show you this thing.
Oh wait, no, it might work. It's got the sled.
Yeah, we'll see. And that's fine for this
Wait, I think
example.
it's missing a sled. I
Okay,
think
so-
it's missing a knot though.
Okay, so I'm going to break right after the call to vuln_func. Okay, that will be immediately after our. Actually, let's not, because you wanted to see why. So let's do vuln_func. Yep. And we'll do it right before the leave ret, so it would be bone func plus 7zor. Okay, and then we're going to run it with Jeremy's solution. What the heck was it called? sol.py? Is that what you called, Jeremy? Did you shebang it, or do I have to put Python 3 in it?
I don't know. I think I
Let's make it.
think I sent it to you in Discord. As a text, as like a message. I don't think it's a file.
All right, and then x slash. All right, so here is our return back to main. I'm seeing the very first 0804 that's not part of Jeremy's drop sled, right? 91D3, we could check that. It would be like this ass star OX 0804. Do you see why I have ASLR turned off on these? So that you can look through that memory and recognize what you're looking at. 919. You may not be able to do it right now, but if you keep this up, you will.
Not sure what it is.
D3, okay, so yeah, that's the return value, right? 91D3. And then immediately before that, our stack on this machine that I'm working on is FFFF, not BFFF, but I can see, because I'm dumping stack, that that's the page it's on. So that's our base pointer, and you can see that we hit it with the 0, 0, right? So before that, it was some larger value, and it would move us farther up into main. And now what we're going to end up doing is jumping. We're going to have our base pointer be right here. So let's step out of this. Good. And now we're going to break right before the leave here. So it'll be break star main plus 25. So continue. There's our second break. X slash 4x cache USP. Where is it now? Doing brain math. Okay, so leave and ret are going to do what? What does leave do? It can be decomposed into two instructions.
EDP, ESP, ESP? No, EDP, hot EDP.
Hot EBP. Right? So ESP is going to go up to where EBP is, making all this garbage. We're getting rid of the locals. ESP, boom. And then we're going to pop EBP. And so EBP will be somewhere up here, except because there's a null there, it won't be somewhere up here. It'll be somewhere in here. Okay? So let's step through the leave. Okay. Now what we have, instead of having the ret to main, instead of ESP being here, ESP is right in the middle here. Right? And those numbers, that's Jeremy's somewhat rock sled. That's a gadget. So where is he returning us to? Let's find out. This ass. 0804 9133. Syntax. Just a ret sled. Why did you do it like this?
What do you mean? It's how it was good.
It does work, yeah. There's a shell. Okay. If we had just put A's in there, what you would see right now is crash EIP equals 41414141.
Could it just sort of like?
Yeah, no, it's perfect. It's very nice. It's very nice.
So I'm confused. When you pop the EDP up, how does it return to the middle of buff? Like I understand like the byte offset, but how does it return to like buff?
EBP is the base pointer, and it's how you reference your locals. EBP minus is locals. EBP plus is arguments, right? So all of the work done on the stack pointer is relative to where EBP is. Now, EBP is supposed to be up here, right? But by overwriting the lower order byte, it is now much lower than it's supposed to be. And it happens to be the case that that lowerness pops it into the middle of data we control, right? And so after you do leave, the next thing you do is ret, you pop where you are into EIP, right? And if you're right in the middle of data that you control, it's going to be arbitrary, whatever you want. Jeremy set it to a set of rets, so it just like walk down. And if we had just set it to A's, it would be all A's.
So is the purpose of the not sled that we like extend the stack sufficiently that we get like when we jump randomly into it?
No. The stack is always the same size. A stack frame is a static size, okay? The point of him doing the ROP sled is actually not necessary. He did it because he didn't want to do math.
No, I did the math at first, but the environment variables changed the place that you load back, so I made it so it was a little bit more robust.
Yeah, okay.
Because you had to return it to the stack.
Yeah.
This one you couldn't do it any other way.
Yeah.
They were like one gadget.
Yeah. There
One gadget.
are other ways to make that work. So what he did is not a NOP sled. A NOP sled is instructions that get executed. What he did is build his own stack frame. And his stack frame is just a pile of return addresses that return to return. And so what he did is, all these are return addresses, and each one calls return. So it goes out, calls return, comes back. Goes out, calls return, comes back. And just walks on down the list, and then he put his actual gadget at the bottom of this. And so that way, if stuff moved around, he had a way to make it line up, right? Why did I show you that example? 1, you learned about off by ones. 2, you can see that a null write, a single byte null write, is exploitable in many situations that it does not appear to be, despite being an extremely restrictive primitive, right? Your first homework example is going to give you an arbitrary write to wherever you want. Write what you want, where you want. This is write 1 byte that we told you, someplace you don't even get to control. Still exploitable, right? This is exploitable because it's lucky, but if it's on the heap, you have control over the heap, right? You are the person interacting with the program. You send the data to the program. The program responds to the data that you provided it, right? It will act differently based on the different inputs you provided. Indirectly, you have control over the program flow of the program as the hacker. And then you use that to get direct control, okay?
We talked canaries. We talked 0 byte. We talked the stack layout for multiple calls. We talked partial overwrites. Okay.
So the first example, the first homework example, you will not need to use shellcode for. If you use shellcode for it, that's fine. But what I'm looking for you to do is just call system. Okay? If you don't know what the system call does, read the man page and find out. You don't need shellcode to own that thing. The principle that you're looking to understand there is that you want the simplest, most reliable across environment solution you can come up with. Okay? Shellcode is more complicated than just doing what you would call a ret to lib. Before anyone needed to do return-oriented programming because of memory protections, which is the mitigation we'll look at after the stack canary, you could just very easily return into libraries. It was a way to make things reliable. It was a way to make things simple. Simplicity is reliability, okay? There are a couple things that I want to cover before Lab 2, but I think what we're going to do in the next class, especially if it gets snowed out, is I'm going to do a history lesson. And this is how the history lesson is going to work. It will be the history of the arms race. This is the first part of the arms race, the stack canary, okay? And so what is happening here is people hack stuff, somebody comes up with a mitigation. And the mitigation targets the way people were hacking stuff. And the way people were hacking stuff is the simplest way to get in. If you ever break in somewhere, you're not going to go and pick all the locks and like wear an invisibility cloak and spend $1 jillion on cameras. You're going to hop the 3-foot fence in the back, right? If someone makes a 6-foot fence, you're going to bring clippers. But you're not going to bring a bazooka. You don't need one. And so when people make mitigations, they're like, I solved it. We beat your fence hopping, right? But what they don't understand is it took them 6 years to beat your fence hopping. And you only hopped the fence because it was the easiest thing. You, in your pocket, you've got 20 other ways to get into this place. You already ready with them, just in case someone is smart enough to make a 6-foot fence. And you were astounded it took them 6 years to do so. And so they spent 6 years, and the very next day you're still in, right? That's why you need to understand this even if you want to be a white hat. Because if you don't, you will fall into the trap that they fall into now and will fall into perpetually, which is spend a great deal of money to stop you from doing something stupid when you have 15 smart things in your pocket, right? And so when I'm thinking about mitigations, I'm thinking, what would really squeak me over? And you don't know that unless you're writing these exploits. If you're not doing this, you're going to waste time and money, and you're not going to get any benefit for it as a white hat, okay? Right, so this is the first one. After that, they said, all right, they figured out how to hop our canaries, but they're executing from the stack. Let's make the stack not executable. That means we've got to go through and add things to the architecture, right? We've got to say, old architecture, if it was executable, it was writable, okay? The technology W XOR X is what they built into processors at that time to add protection so that you can execute from a page that wasn't writable. If it was executable, it couldn't be writable, right? That's new. They had to add that to the hardware. The operating systems all had to implement that in the page table, so they had to rewrite all the page table code, okay? Now, you can't execute from the stack. You can still ret to lib. And if you've been doing that in the first place because it's more reliable, it didn't slow you down a bit, right? If you were doing it right in the first place, not relying on those stack addresses, when they said you can't execute from the stack, you were like, wasn't doing it anyway, right? And so that's where ROP comes in. That's the next part of this chain. And ROP was extremely simple, right? Because everything was always where you expected it to be, right? And then, so then ASLR comes after that. We'll talk about it, and I'll walk through the whole thing from the year 2000 to current day with control flow guard, how you beat control flow guard, and XFG, which is extended control flow guard, which I worked on at Microsoft for the year that I was there, okay? And the limitations of XFG, and probably why even the Windows hackers here will never see people run XFG. Because at a certain point, the cost of getting the mitigation to work is higher than the cost that you pay out when you get hacked, right? Here's optional auxiliary homework. Read the news. Find a company that got hacked. Look at their stock price. Then look at the stock price in 2 weeks. And what you will see is that. People think about it for a little while, and then they forget about it instantaneously. And if you buy the dip, you make money. So every time that my company got owned, I was like, ESPP money. Right? Right?
Wait, is that what
The market pressures to move fast and make money are more important than security. The reason that I am here teaching you is not because I want to make a bunch of money as a teacher, right? The reason I'm here teaching you is that code is infrastructure, okay? Code is bridges, code is roads, code is air traffic control. Code is what keeps the lights on in Abbottabad and the anti-aircraft guns running before you bring 2 Black Hawk helicopters out. All of that is code, right? For civil engineers, is there anybody who has civvy friends here? What are they studying for? More than that, there's a test they're studying for. They need to get certified, and their designs need to get certified. Because we realized if we just let people randomly build bridges cheaply, they fall over and a bunch of people die. So now we have rules. We don't have any of that for code. Okay? It does not matter if your code is infrastructure code or random code, because infrastructure is whatever is there. So are people familiar with how Ukraine is getting its internet right now?
Starlink.
Starlink. Is Starlink an industrial, protected satellite network with DoD encryption, or is it some random shit that Elon Musk shot up into space for the cheapest amount of money you can? It's that second one, right? Why are they using it? Because it's the only option they have. Every piece of code you use becomes part of that stack. In your other classes, you learn to use APIs and libraries, right? You know how they work? Not really. You call them and they answer you back, right? Did those people build those APIs and those libraries to be war ready? Or did they just build them as cheaply and fast as they could because their boss is breathing down their neck and they're 60%, they only have 60% capacity and they're not getting backfills. And so now, 6 people are doing the work of 10 people. It's that second one, right? Someday, someone else who doesn't want us to do well is going to realize that's the case. And we have been doing it to other people now for 2 decades, right? What happened with Stuxnet? What was the point of Stuxnet?
Didn't they get the, I forget what it's called, but the things that spin, to keep spinning and spin really fast till they all shut down?
It's to shut down the Iranian uranium centrifuges for like processing and enriching uranium.
For enriching uranium. It was industrial espionage. The goal is they have to spend a lot of time and money to make nuclear material. Foul it. And that's what we did, right? At some point, somebody else is going to realize that our country is built on all the same garbage, right? And if they want to turn off their electricity, a group of people about this large, knowing what you know now, after doing lab 1 and doing these 2 homeworks, is capable of doing that. Okay? And so what I would like is for you people to know things that my generation did not know, so that when you go and build infrastructure, you build it right. Because when I'm old, I'm going to be pissed off if my electricity is turned off. Right? So I am building effective white hats by building effective black hats. Okay? That's it. We're a couple minutes early. The grad seminar we're going to do in this room immediately after, and we're going to look at vtables. And you may or may not see vtables in the code that you write for the grad project. I spent this morning writing 5 or 6 or 7 different vtable examples to try to figure out exactly what the compiler was going to do vis-a-vis vtables. And what I found out is it's extremely variable, which is going to be a great lesson for you, but we're going to have to look at all the possible options so that you can kind of recognize what they look like.
Could you go back and show me the instructions that writes the null byte at the end of binsh? I missed that when I was writing.
The instruction that writes the null byte at the end of binsh is strcpy. So it's in strcpy library.
She's talking about in the shell code.
Oh, in the shell code. I can pass out Jeremy's example. I stole it from my parents.
Also, with that stack, that bug not working, there, I switched the stack pointer like before.
Yeah, that's why it's not a homework.
It was just like very lined up.
I lined up.
Like shit that like but if you can overwrite the return address, leave brackets there, you can see
Jeremy, all right, one more thing, real quick. I got 10 minutes. I'm going to tell you why I don't like Jeremy's answer to this question.
Other than the really janky stuff.
I'm picking on you because I know you can take it. We already did all the homework. All right, okay, check this out. This is very bad for you to learn from, and if Jeremy, this is what we're going to do. At the end of class, on the final day,
I'm gonna be like, I'm gonna mess this up a little bit, and I'm gonna be like, Jeremy, fix it.
I won't be able to do it.
You won't be able to do it. Why? Because he did the math elsewhere and he didn't write it in here, right? What he said is, oh, I've got X number of space for this buffer. It's 256 bytes. 256 divided by 4 minus the size of my EVP that I'm overwriting so that it lines up exactly at 256 happens to be 57. He did it in his head and then he wrote it down there. That's great. What you should do is let the computer do the math for you. You should be like, what's my buffer size? 256 or hex 100. And then you do the math. You're like, pointer size is 4. So bufflin minus 4 times blah. And put the logic and the math in your example and split it all out into variables, right? When you looked at the lab 1 example that I gave you, it's got a bunch of variables at the top, right? That's so that you can just change stuff and then all of the math works out. If he changes one thing, he's got to rewrite the whole problem. Let the computer do the work and let the code be your documentation, right? That's also why we don't write 93910408 backwards, right? We let struct pack do it for us, so we can just see the numbers, so that we can do the math in the code. So do the math in the code, or I'll take points off, because you are going to just make yourself suffer later, right? Cool? Sorry, thank you. Actually, that was a good example.
It's so pretty though. It's all one line.
Yeah, it's all in one line. What would your other professors do if you turned in your homework and they were like, write a linked list, and you're like, it's so pretty, it's all in one line? It was like, get out of my class.
Yeah.
Mary is below it.
There was a class that loves that.
You would be fired at a job for doing that. What would happen, and this is what happens. You write all that code and it works, and your coworkers have to go fix it later. And before you come in one day, they have taken all of the furniture in the entire office and wedged it into your cube. And it's like 500 pounds worth of furniture. And then they're like, "Have fun getting that out of there." It's about as fun as us figuring out your one line of code. Right? No, it's not good. You're going to have to work with peers. When you are writing real exploits, the phase from EIP to a reliable exploit can take between 6 and 8 months, right? That 6 and 8 months, you might have a vacation in there. You're going to come back and look at that, and you're going to hate yourself, right? Use your notebook. Write down every step of the way. What happens if Jeremy gets halfway through this? It's working, it's working, it's working. He makes a typo and screws it up.
It happened.
Did you have to start over?
No, I think I figured it out eventually.
Eventually. A lot of the time you have to start over from nothing. So break up your solution into logical pieces that say, I have built this primitive, save it off in your GitHub, write a comment, okay? Now I work at the second primitive, and you build it up slowly in that way so that if you get lost, you roll back to the last logical place that makes sense. You don't have to start over, right? And that also means find a way to externalize your brain onto pieces of paper, right? We're going to be working with a lot of breakpoints, right? You saw me sitting there going through this being like breakpoint, 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 right? Those are just random numbers, and if I restart GDB, they all go away. You can put them in a script and like load scripts into GDB, and I would encourage you probably to put your breakpoints in like that. Put comments on your breakpoints. The reason I set this breakpoint is X. This breakpoint allows me to verify this assumption. If the assumption is true, this is what will come out when I look at that memory. Otherwise, I have a disconnect between where my assumptions lie and reality. And it's my job to figure out, using the debugger, where that lies, right? And so the way you do that is you start from a place where you know what's going on, and you walk through and verify until you get to the place where it doesn't work anymore. And that helps you to identify where that disconnect is. If you can't roll back to a specific place, soon you got to roll back to the beginning, right? I'm saving you time and effort here, okay? This is stuff that I learned by burning myself hundreds and hundreds and hundreds of times, right? And I want you to not get frustrated on these homeworks.
That second homework is hard, okay? That second homework is going to require you to write a little bit of custom assembly, and you're going to have to write it in a text file and run NASM and dump it out as a bin and pull that hex out. We talked a little bit briefly, there was a question asked, I think you asked it, about what happens when your ESP is in the middle of your shellcode. You can't call functions without overwriting your shellcode, right? Because you're pushing. So you're overwriting wherever ESP is. And so the solution to that is to write a little bit of custom assembly at the start of your shellcode, sub ESP some number, get ESP out of the way. You're going to have to do something like that, not that specific thing, but something like it, in order to solve that second homework reliably. Okay? You're going to need a negative relative jump. And you'll have to write it yourself and put it in there. The reason is I didn't give you enough space for the shellcode on purpose. Okay? A lot of people are like, we want to go to the heap, we want to go to the heap. We've done this stack stuff. Does anybody take differential equations? How many differential equations problems have you done out of the back of the book?
0.
Are there any good students?
On the shitty Pearson website.
Oh, when I took differential equations, I was bad at it. And the way I got good at it is I opened the back of the book and there's 1,000 problems. And every day you're like, I'm going to do 100 problems. You have a graph paper, you do 100 problems. That's what we're doing with this stack stuff. Until you understand the simple work in the simple case, when we go to the complicated case, you're going to trip all over yourself. And a lot of problems are small aggregations of simple problems. That's what becomes a complex problem. This computer is a binary thing. Those instructions are extremely simple. It becomes complex in aggregate when I put hundreds of thousands of those things together, right? Like when you first learn about computation, this is a binary system. There's only 2 values the computer can store, 1 and 0. And it boggles the mind that you can do arbitrary work with that thing. But it's because you build it up slowly from simple pieces, right? The complication is in, now I've got to digest 1 billion simple pieces and figure out what's going on. That's the problem with reversing too, right? So stick with these. I'm going to show you some hard shit that you're going to be able to do with the stack stuff. And then when we get to the heap, you'll be ready to do it, okay? No? Okay. Any other questions?
We're just saying homework 2 is going to require this. Is that like example 2?
Yes, example 2. Yeah. There's example 1 and example 2. Example 1, write what where, doesn't need shellcode. Example 2, that's my test to see you can do example 2. If you can't do example 2, don't feel bad about it. Write down your work and your thought process and how far you got and where the disconnects happen. If you can identify where you're confused in example 2, that's still an A, right? Here's why. Probably you're going to work with 5 other people. And those 5 other people are going to be working on their own problems. And so part of your job as a hacker is to be able to go to the smarter person in your group and be like, I have 20 minutes to explain to you this problem so you can tell me what the solution is. And you have to get the entirety of your problem into their head, right? So if you can cut that down to be very specific where my disconnect is, you can do that. But if they have to go and open your debugger and look at it, they're going to be like, sorry, I have my problem in my head. I'm not going to dump it out so I can load your problem in. Mine's part of it, right? And that's part of it. Cool. I think it took Zoe, have you done X2 yet?
Not yet.
Has anybody done it yet? 1, 2, 3, 4 of people who are already in the class or have jobs and are grad students. It took Zoe 1.5 hours. She's real fast. Cool? All right, now it's grad student time, undergrad student.
When I was doing workout for X2, I literally went to the math major floor. I was just like scribbling something.
I did an audio tape that. I wanted the audio out of the piano.
I know, basically.
It's like, you know, it's like when you see our French.
That's right, it's all on the YouTube.
You can always take out the audio track from the file.
Can you do that for me?
I could, yeah.
Okay, yeah.
At least like with the
Yeah. Okay, make up your mind.
I love it when you don't let that happen. Yeah. I love it when I don't want to do what I want to do.
I see.
Yeah, try it again.